So I will continue with my um, OneNote screen presentation. Okay, but since there's a second half and it'll appear a separate recording, what I will do is I'll split this. I'll create a new PDF file. Okay. All right. So we were looking at waves, and hopefully before the break, I hopefully convinced you that that there was we encounter oscillations. Okay. Now we have to ask, how does this oscillation, what do these oscillations tell us about instability? Okay. So again, yeah, the idea is quite simple. Okay. So let me do oscillations to instability. Let me just give it a title. Waves instability. This is across the scales, small scales to large scales. We saw examples of small scales. You saw things like a tiny droplet being held upside down when it was heavy. It was this, if you remember this experiment where you had this tube and the fluid would not flow down from this. This was heavy and this was light, and that's because there was surface tension here. Now this is unstable system, inherently an unstable system, but it is stabilized because of surface tension. Okay. Now, what's the connection between waves and stability? Now, let me illustrate this again schematically. So let's say we have created a wave on the surface. Okay. Now, how do I create? Let's say this could be the surface of a calm lake or pond, or it could be just the water surface in the bucket of water that you have at home. Now I can create these undulations up and down, and when I create these undulations, then eventually if the undulations are small, okay, then what will happen is that these undulations will die out eventually. Okay, this is governed by largely like a system which is like the spring mass damper system. Remember the spring mass damper system? It is mu double prime plus gamma u prime plus ku is 0. So k is like the spring constant. K is a spring constant. In this particular case, gravity or surface tension, they will act like a restoring force. Okay. K gamma is a damping. So normally, whenever you have a driving force and a restoring force is something that opposes that motion, then you have an oscillation. In the simple pendulum is another example. It's a very beautiful example of, here's my pendulum in the original state, equilibrium state. And if I give it a push, and if I take it here, then this flow will oscillate back and forth between these states. This oscillation, you can again represent it like a sinusoidal wave in time. Okay, correct? So if you plot angle versus time, it will be like a sinusoid. Now you see that I'm trying to draw connections between what we see as oscillations in space and this pendulum. In pendulum, it's not oscillation. It is pendulum is physically moving back and forth in space, but I will get a curve like this when I plot oscillation, when I get it in time. We think of these as oscillations in time. They're fundamentally related, oscillations in times and oscillations in space. Okay, because fluids have a finite extent. Okay, and because they have an extent, you can see literally these oscillations in the form of hills and valleys on the surface. Okay, now if I were to have, it's possible that if I have some wind, okay, if I have some wind, then it's possible that this wind is going to create low pressures and high pressures on this. Typically what it'll do is it'll create low pressures here and high pressures here, high pressure and low pressure. Okay, now if this low pressure is sufficiently low, then what's going to happen? It's going to create a suction. These crests will go up, and when the crests go up, then the trough has to go down. because the mass has to be conserved, right? So what will happen, I will show it with a different color. It's possible that this wave is traveling, so therefore the nodes need not be the same, but the amplitude is slightly more. Okay, and it could be even further. So if the conditions are just right, then what could happen is these these oscillations can grow. So how do I know that this is growing? One way to do this is I can monitor the size of this crest. I make a plot of how this crest is varying with time. Okay, if I get rid of these things for now, I can make a plot of how these crests are varying with time. So I'll say this is crest position with time. Okay, and it's possible that I will see if it is growing, then I will make a bunch of recordings like this. This is highly exaggerated, by the way. Okay, I mean, this is the y-axis that I've drawn in this crest position. I have not given any numbers here, so you can scale it any way that you want so that the curve is visible. Okay, so eventually you'll get a curve like this. T equal to 0 is representing the start of the experiment. So when there is no wind. So once you start wind, then you have this, it grows like this. Now, if you're in the linear framework, you will find almost always we find that this position, let's say I call it as y will go as exponential something times t, where the something, this quantity here, we call it the growth rate. Okay, this tells you that the wave is amplifying with time. Okay, but notice that it's also doing something else. While it is amplifying with time, it's also amplifying in space because it is also flowing down. Correct? So it is also flowing down. So where is this now? I can ask a bunch of related questions. Where is this energy coming from for the wave to grow? Who is providing the energy? Naturally, if you see here, the energy is coming from the excitation that I have given. This is the wind, correct? So the wind is giving the energy, and the wave, what is it doing? The wave is taking that energy. So this is this is a good way to think about it. The wave is as if the wave is taking that energy and it is growing at the expense of the wind. So the wind will lose some of its energy, but we are thinking of a large amount of wind and a tiny wave. Okay, so the amount of changes in the wind energy will be negligible, but you can see appreciable change in the shape of the wave. Okay, so you can when we talk in this language, we can talk about what are called as amplifiers and oscillators. Okay, so you can divide all instability problems into these two categories. Ones which are called amplifiers, the other which are called as oscillators. Okay, so I hope people are able to follow me. Okay, so I can have this classification. Okay, what is an amplifier? What do you think is what does an amplifier do? Amplifier something to amplify something, you need to give a signal first, correct? You give an input signal, the input signal amplifies. Okay, it will increase in intensity, as Dr. Jitu Babu has just said. The signal strength is increased. So in the same way, in the context of fluid mechanics, instabilities, what is really happening is that this wave is basically taking energy from the mean flow or the wind, and growing in intensity. Okay, it's increasing. So it's an amplifier. But you can also have situations which are a bit more complicated, but you can have situations where the wave will once a wave has grown to a certain extent, once an instability has begun, it will oscillate. It'll create, there is an internal dynamics that will take over on its own, and it will continue to oscillate. It'll have a self-sustained oscillation. Okay, so this is this is one way to look at it between amplifiers and oscillators. But there's also another way to look at it, which is, I was talking about space and time. There's one classification. Another classification is absolute. Sorry? Somebody said something. 1 second. Yeah, somebody asked something. Sorry, I couldn't hear. Okay, so feel free to unmute yourself and speak. There's also something called an absolute to convective instability. Okay, now how do we think about absolute and convective instabilities? In this example, I said the wave is growing, but it's also flowing down with time, right? So you can have a situation where if you give a disturbance, the disturbance will basically keep amplifying. Okay, how do I think about it? So let's look at 3 scenarios. Okay, the first scenario is where I have time and space and time. I'm giving a disturbance. Okay, what is the disturbance? Let's say I give disturbance. I will give it like a wave packet. I'm giving it some disturbance. This is a representation of a disturbance. This disturbance, as you wait in time or you wait downstream, then this disturbance, it's a little tricky to make this drawing. This disturbance is decaying in amplitude. Okay, this is what we call as a stable system. This is linearly stable. Okay, now we can have a situation where I give an initial disturbance at t equal to 0 or very close to t equal to 0. I give an initial disturbance. After some time, the disturbance is just growing like this. So this system, I can make an envelope like this. The system is unstable. But it is convectively unstable. Because the disturbance will grow, but it will keep growing downstream. It will not grow there only. It'll amplify downstream. One example of convectively unstable systems is basically you have this boundary layer. You have a boundary layer of flat plate. You have a fluid coming like this. You have no slip condition, and you have a velocity profile like this. Okay, this is a flat plate boundary layer. This system is unstable, but it is convectively unstable. What I mean is, if I create a disturbance here, this disturbance will grow, but it will grow downstream. You saw, you got that? Now the example that we saw in the Reynolds original experiment that you saw the video, you saw those waves that were there. That is again a convectively unstable system, which means that the waves are going to amplify, but they're going to amplify more and more as you go down. Okay. Now, these kinds of disturbances, you can represent it in this space-time diagram like this, that in these regions, away from these, within this envelope, this envelope, you will see this as instability. Okay. You can calculate an average average rate. Okay, like average rate is basically the slope of this curve. Okay, the slope of somewhere in the middle. This is what will give you what is called as a group velocity of this wave packet. It will tell you at what rate the wave is traveling down and it's growing. Okay, in this group velocity, in this case, is complex because it's amplifying and also traveling. Okay, now you can have some systems where the amplification.
Hello,
Yes, yes.
sir. Yeah, sir. This convective unstable system, or
Yes,
it's grow in downward stream, right? You told. So
yes,
whether
it is
it
growing in downwards
will
direction.
whether yeah, my question is whether it will mitigate after some time, or it will grow indefinitely, or what will
Well,
be that?
okay. So well, I wanted to come to that question after this, but can we come back to that question
Yeah,
after another
no,
point?
no.
Because it's the same answer for absolute for, and I'm going to talk about another kind of instability. But for both of them, it's the same common answer. So I'm going to address both of them in one shot. Okay. So there's another, but let's please tell your name when you ask the question so that I can actually address you with your name. Okay. So who was that? Sorry,
Jaydev. My name is Jaydev.
Jaydev. Okay. Thank you for that
Yes.
question, Jaydev. So we'll
Thanks.
will there's another kind of system that can happen where you give a disturbance. Okay. You give an initial disturbance. After some time, you'll see that it'll keep growing like this. Of course, it's challenging for me to. This is of course this is a sketch. Okay, I'm just drawing it. I'm doing a freehand drawing. Okay, without any practice. It's been a long time since I've made these drawings. So this is growing. Now you see that where it's growing. It's growing at the location where the disturbance originated. Because if x is the location where it originated and x is equal to 0, it is growing there itself. It's not the instable disturbance is spreading around it, but largely disturbance is growing there. Okay, it does not matter whether these two and the envelope that I've drawn with these two lines, they are exactly the same or not. They are at the same angle, tilt angle. In general, it won't be. Okay, it's possible that this envelope may even look like this. The envelope even may look like this. Only thing that matters is, does this envelope cover the original location x is equal to 0? Is x is equal to 0 covered inside? If the envelope is engulfing the x equal to 0 location, the original location, then it means that the disturbance is growing there itself. Okay, this kind of an instability is called absolute instability. Okay, we saw that example of a vortex shedding, right? The vortex shedding, once the instability starts, the instability is self-sustained right there. Okay, so it becomes it's an oscillator. The vortex shedding instability, if you basically the carbon vortex sheet, here is a body, and here you have a mean flow. And what you saw in the, if you remember, is we saw images like this, right? Now, if you take a pressure probe, if you take a probe anywhere, let's say you take a probe like this at this location, and I plot how does the velocity at that point look like, or how does the vorticity look like, how does the pressure look like at that location. Okay, it's very easy to get pressure probes. If you plot at that location, how does it look like? You will see that the pressure will be nice oscillating. Okay, this is an oscillator, and further the instability is contained there itself. It's an absolute instability, what you see in the system. Okay, so now the question that was, I think Jaydev, right, he was asking, what will happen to this now? This is unstable. When I say this unstable, what is happening is, okay, I said pressure probe and you see an oscillation, but this is not what really happens at the start of the instability. What really happens at the start of the instability, and this answers the question that Jaydev was asking. Okay, I can think of a thought experiment for this. The thought experiment is, I basically have, I have this cylinder, or I have an object like this, and I start increasing the speed. Now, if I know the velocity, if I know the density of the medium and the viscosity of the medium, and if I know the size of the body, let's say I call it as D, I can come up with a number, the Reynolds number, which is rho u d by mu. It tells you the ratio of I'm sorry, ratio of inertia to surface tension, inertia to viscosity. Okay. Now, if you do this at very low speeds, if the Reynolds number is below a critical value, okay, then if any disturbance that is created, there will be no disturbance at all. And even if you create a large scale disturbance, like you shake the entire body or do anything, the disturbance will die out. Okay, so below a critical Reynolds number. So this is vertical will be, okay, horizontal is Reynolds number, vertical is the growth rate. I'll tell you what is growth rate again. But below a certain critical value, the growth will be negative, which means that any disturbance that you give will die out. So the lower the value of Reynolds number, lower is the growth rate. Okay. So you can take it, and lower will be, and it will be negative. Okay, that's why you have these negative. This is negative. Here growth rate is 0. Okay. Now, because you can imagine that very easily. As the Reynolds number becomes very small, what are you doing in the expression for Reynolds number? The viscosity is becoming more, and viscosity inherently is a damping quantity, right? You are increasing damping over inertia. Okay, damping will kill oscillations, so therefore it will die out. But beyond a critical value of Reynolds number, typically in an experiment, what we do is, as we keep increasing the speed of the fan, okay, beyond a certain value, you will start seeing that there will be growth. Okay, now I can connect all these points and I have a curve like this, from which I get what is the value of critical Reynolds number, Re critical. For example, for a sphere, or for a cylinder, I don't know, maybe I think cylinder. Okay, for a cylinder, Re critical is around 46. Okay, so at this any value above this Reynolds number, you will start seeing oscillations. You will start seeing vortex shedding. Okay. Now, what is what will be the answer to what Jaydev has asked? Now, how do I get this growth rate curve, and how do I relate to what the question was that Jaydev has asked? Now, if I get oscillations, I get these oscillations, and I put a pressure probe, and I plot how does this pressure vary with time. Initially, the moment you start the experiment, you're not going to get vortex shedding. It's going to take some time. How does that curve look like? Okay, that's the curve that I'm interested in. So to see how does that curve look like, I will plot, let's say, any quantity. It could be pressure or any other quantity. You start the experiment at t equal to 0, which means that you switched on. Typically, we do these experiments in a wind tunnel. You put an object in the wind tunnel and you put a pressure probe right behind the cylinder, and you have a wind that is coming from, let's say in this case, it is coming from left to right. Okay. Now, what will happen is I can plot the pressure. Initially, I'm looking at fluctuations in pressure, not the absolute pressure. Absolute pressure also I can plot, but I'll look at fluctuations in pressure from the mean. So the pressure, it will start from 0. So initially there'll be no fluctuations because there's hardly any detectable thing. And as I keep increasing the speed, then this fluctuation, and then I hold the speed at a certain value, then you will start seeing that these fluctuations will increase. Okay, my curve unfortunately became bad, but it does not matter. Okay, now you see, I can put an envelope around it. This envelope, this is pressure fluctuations, will go like exponential of some lambda times t, where lambda is the growth rate. Okay, now remember this is an exponential curve. What do you know about exponentials? Exponentials grow faster than any polynomial. Okay, exponentials will go faster than absolutely any polynomial, and because they go faster than any polynomial. Just one second. Because they grow faster than any polynomial, there is no way we can actually have. I mean, the oscillations can become huge. Okay, because when the oscillations become huge, you cannot sustain it. Okay, you cannot have large pressure fluctuations. Now think about it in a wind tunnel. You're talking about pressure fluctuations, but pressure fluctuations about a mean value. The mean value is typically the atmospheric pressure that we have. You cannot have pressure fluctuations that are so large. If they're so large, then the entire equipment will just break. Okay. Typically, what will happen in these systems is this exponential oscillations cannot be sustained. The fundamental simple reason why it cannot be sustained any further is because where is the energy coming from this growth? It is coming from the fluid itself. The flow, the wind itself, meaning the flow, when it is growing, the wave is growing, it is sucking the energy from the surrounding air. Okay, so the surrounding air is losing some of its energy, kinetic energy, and it's giving into these disturbances. These disturbances are growing. Now there is only so much of energy available, which means that, and the process also becomes very inefficient after a point. It cannot suck energy anymore. So what will typically happen is, after reaching a large amplitude, the system cannot grow exponentially, it will stabilize. It will stabilize. So you have the system. This here, from here onwards, once it is stabilized, this region we call it as nonlinear saturation. It will the disturbance will amplify and eventually saturate at some nonlinear value. What is the exact value at which it saturates? That depends on a variety of points, like what is the boundary conditions, what is the parameters of the problem that you've chosen, and so on. Okay, but I hope that answers your question. Fundamentally, whatever these disturbances are, they can keep growing and eventually they'll have to saturate at some point. They can't keep going forever. Okay, in the pipe flow, for example, that we looked at in the Reynolds pipe flow experiment, these disturbances can grow, but there is a limit, right? How much they can grow? They cannot grow more than the pipe itself, right? So that is a nonlinear saturation that you see. Okay, so okay, we've continued the language of waves, but now you see exclusively in these last few examples that I've talked about, exclusively the fluid examples. I've moved away from simple mechanical systems like a spring mass damper. I'm talking about mechanical systems. Okay, now if you were to believe, if you are a true believer like me, that a large class of fluid mechanics can be described by Navier-Stokes equations, then what we will do is, it's a good starting point. I mean, you need to have faith in the Navier-Stokes equations. The Navier-Stokes equations have been tested again and again and again in a variety of different experiments, and it's a very accurate model of fluid behavior. Okay, so if we use that as a starting point, let's basically write down the equations of motion first. Okay, and I'll make some simplifications, but we'll write down the equations of motion for a fluid, and then we will do some analysis with that. Okay, Is everybody clear?
Yes, sir.
Okay. So we will primarily do this. We will be doing this analysis for laminar flows. Okay. And we want to ask, what is the condition of stability? Okay. Or if not, even if you're not able to tell under what conditions stable, we can at least tell under what conditions it's unstable. Okay. Those two are not necessarily the same. Okay. We can at least tell what conditions a flow becomes unstable. Okay, so I'll use a quote that Landau and Lifshitz. If you've basically heard of those names, they have Landau and Lifshitz had a very famous quote in their book on fluid dynamics. He says, not every solution of equations of motion, even if it is exact, can actually occur in nature. Like you may, those who have done fluid mechanics, you would have learned that the standard example for a pipe flow in a pipe or a channel is the nice parabolic velocity profile, correct? But in reality, we will not see that. Only under careful controlled conditions can you see that. If you just do a random experiment at high speed, you will not see it. The reason is that it is not necessary that this parabolic profile is a solution of the Navier-Stokes. It satisfies the Navier-Stokes equations, but that is not enough. The flows that Landau and Lifshitz go on to say, the flows that occur in nature, okay, must not only obey the equations of fluid dynamics, in this case the Navier-Stokes equations, but must also be stable. Okay, right? So, okay, there's some questions on Karthik Selvakumar is asking, at what point the failure of a component will happen in a nonlinear oscillation? Well, that depends on the nature of the component. For example, you can have gas turbine where you can actually have an instability that comes in a gas turbine. We have Professor Sujit at IIT Madras. He has done some pioneering work on this problem, on this class of instabilities called the thermoacoustic instabilities, which actually result in catastrophic failure of gas turbines. Okay, but at what conditions do you see that depends on a variety of questions. What is the nature of the instability? What are the experimental parameters that you're operating at? Also, it depends on the structural stability of the gas turbines, of the component. Okay, so it is not an easy question to answer. There is no one answer to at what point can a failure. The point at which failure will occur depends on when it's possible that there's no failure at all. You could just have nonlinear saturations and the flow becomes turbulent. Nonlinear saturation does not mean there could be failure. Nonlinear saturation could mean that it has gone into another state. Remember, you can think of fluid mechanics as ultimately you're having a differential equation and you're solving for the differential equation. The differential equation, what you see is a solution of that equation. You could go from one solution to another solution. It doesn't necessarily mean that the other solution, which could be a turbulent solution, necessarily is bad from a structure's point of view.
Sir, actually, sir, can I speak?
Yeah, please.
Actually,
who is this? Sorry.
This is Dr. Karthik.
Karthik, yes.
Actually, you have said about in fluid mechanics, like in fluid, I am working with fluid elastic instability. So there is a certain condition time period that fluid elastic instability nature will occur. The failure of component, which I am observing at a certain velocity or.
You're seeing a fluid elastic instability. So this structure will oscillate, and eventually at some conditions like a resonance condition, it will fail.
And one more thing, you said about that is a saturation point for non-linear period. After non-linear saturation, it will become turbulent. You are saying, but if it is
no. Whether it becomes turbulent or not is a big question.
Okay.
So we'll come to that after your question.
Okay. I'll follow you.
No. I mean, you have. It need not be turbulent. I don't know. I know that this simple wave-like solution will not be there anymore. That much I know.
Okay.
What it will go into, I don't know. Okay. So, for example, you could have nice, elegant vortex shedding, right? You have a nice smooth flow, and then when cardamom vortex shedding that you got these vortices, a positive and negative. Those vortices need not be turbulent. Those are still in the laminar regime.
But
Because
once it is attains saturation point, you're saying after that the curvature and everything will be same. So if it is not any difference from the other curve, so what will be the effect? If it is a saturated, means there will be a flow will be normal. You are saying it may not be turbulent or it may not be laminar. But at a saturation point means it attained the saturation point. Beyond that, it won't affect. It won't have any effect on the particular thing. That means saturation point we have to know now.
No, see what I'm say. Okay, we know what is laminar flow. Okay, again, laminar. We at least we know what a turbulent flow is. We know for sure that a turbulent flow is not laminar. Okay, that much we know. It's difficult in these boundaries, these in between regions. It's difficult to be precise about what it is. Turbulence has some definitions for turbulence. That there has to be a range of scales. There has to be a strong amount of vorticity. It's highly vertical. Okay, and one can even if you at very high Reynolds number, typically you will get a cascade and so on. There are some definitions. Now, a typical vortex shedding that you see, like the simulation that I showed you, a simple simulation where you saw positive and negative, red and blue vortices, that is not a turbulent flow because you don't have a range of scales. Okay, it need not be called a typical laminar flow. Okay, it's not a layered flow. It's in the simple sense. Okay, so what do I call that flow? Well, in fluid mechanics there is laminar and turbulence, but there's a whole range in the middle sitting which is called a transition. So you have laminar and turbulence, and there's transition. So because this word came up, I mean initially I didn't have a plan of saying this, but in the early days of development of fluid mechanics, especially stability theory, people observed that there's turbulent flow. Like Reynolds did this experiment, beautiful experiment, where he saw this. You go from nice directed motion, as he called it, to a sinewy motion or sinuous motion. Okay, and the natural language was waves. You see, these waves are amplifying, and a lot of work happened in boundary layer theory in Germany, in UK, in United States in the early part of last century. The people started connecting it to waves, and there was a lot of work on waves. Okay, Heisenberg, the famous physicist, his PhD was also on waves, on stability of fluid flows in pipes. Okay, now after a lot of fundamental work in waves, people thought if I study how a flow becomes unstable, maybe I can tell something about turbulence. Okay, so those were early days where people investigated stability to understand how the flow becomes turbulent. Okay, now for a long time, that idea, after a lot of effort, people go from laminar flow, nice smooth flow, to a not so smooth flow, but they necessarily was not turbulent. So people were not able to make the connection. But there has been, in the last 25 years or so, there's been a sort of a revival of these ideas again, especially with the resurgence of the so-called transient growth or algebraic instabilities. Okay, a pipe flow, for example, is not stable. Is always stable, linearly stable. If you just do a stability analysis of a linear stability analysis of a simple pipe flow, parabolic velocity profile, you will see that the linear stability analysis will conclude that it is always stable. Always. But how do I see turbulence in it? So people needed other explanations to do that. So then there's this whole range of flows between laminar and turbulent which are transition. Okay, which need not be turbulent. Okay, also when it comes to these failures, as we will talk about, there are some systems where that failures can happen, like for example thermoacoustic instabilities. Fluid elastic instability is a very classic example of fluid elastic instability, and I should have put that perhaps, is this what is this Tacoma Narrows Bridge collapse. It's a bridge which is open to the public, and then heavy wind started flowing within a few months after opening of the bridge, and the wind actually exhibited fluid elastic instability and it collapsed. because there's a coupling between the elastic modes of the bridge and the fluid modes because of vortex shedding, and then this coupling led to massive amplification of the bridge oscillations. It led to failures. But there are some systems where failure need not occur, but it can just be an oscillation, sustained oscillation. Okay. And sustained oscillation, I mean, you can say, well, eventually some systems will fail because even if there are sustained oscillations, like for example, our electrical wires, as I told you, okay, an electrical wire is basically between, it's like this. If I were to make a simple picture of an electrical wire, it would be like this. There's an electric wire. When fluid goes around it, okay, you actually will have tiny vortices. Okay, these tiny vortices is what you hear, and if you are standing next to it. Okay, these wires are designed to have not fail, at least for a very, very long time. Okay, so just because an instability has reached nonlinear saturation doesn't necessarily mean failure. It depends on, as I told you, on the structure itself. Because in the case of these wires, they know that there will be these oscillations, so they will build it to account for these oscillations from the very beginning. Tall skyscrapers also weave left and right. They are built to oscillate. They are actually, if they don't oscillate, then there's too much of stresses at the joints. So they are meant to weave left and right. Very tall skyscrapers, but they're meant. But of course, there's some stabilizing that is done. Usually, there'll be a spring mass damper in the building to control the oscillation. But what I'm trying to say is that while the oscillation is inevitable, that doesn't necessarily mean there is going to be failure. Okay. So Jayadevan, you asked which book were you refer? You wanted to name a book. You wanted me to name a book.
Yeah. Before that, I just want to ask one doubt, sir.
Yes.
So
Yes.
I think this is what I understood, that this region of laminar flow is defined by where this instability grows or not, right? If this instability grows means it kind of a transition. Am I right?
Yeah, it is transitioning from that linear stable system. From that stable configuration, it is transitioning to something else.
That may lead to turbulent flow, or that may sustain. Right?
Yes, it may lead to a different. So what it really means is, it's going from linear, that one flow to another flow configuration, but you don't necessarily know what is eventually the outcome, because you're limited by the fact that we do what is called as a linear stability analysis.
Okay.
Sir,
the book that you have told one quote from that book.
Oh, this is Landau and Lifshitz.
Okay.
I think it's just called Fluid Mechanics. Okay, it's a difficult book to read. It's a classic book. Landau and Lifshitz wrote many books. They're called A Course in Theoretical Physics. They have books for all the major areas of physics: statistical mechanics, elasticity mechanics, fluid mechanics, and electrodynamics, and so on. One of the books is fluid dynamics. Okay. Typically in the Russian tradition, physicists study fluid mechanics. Okay. Historically, I don't know what is the current situation now. Okay. So let's look at instabilities. Now I started about Navier-Stokes equations. Let's start with Navier-Stokes equations. What are the Navier-Stokes equations? Okay. I'll assume you know the Navier-Stokes equations, or even if you don't know, even if you're not, even if you don't work in fluid mechanics, you can still follow the general principles. Okay. So let's start with Navier-Stokes equations. What are they? So you have mass balance, which is called as a continuity. Okay. I will write it in 2D. 2D Newtonian incompressible flow. I'm talking about a system like this. Okay. Only for the system, you can extend it to more complicated systems. Okay. So you have del u by del x plus del v by del y is 0. Okay. Then you have density rho del u by del t okay. Okay, this is the longest equation I'm going to write in this lecture. Okay. Now let's look at this equation and let's understand what is this equation. This is I'll we'll give this equation a name, a number first. Okay. Maybe I'll just move this out here. We're writing it for a 2D Newtonian incompressible fluid. Okay. Now this equation will give it some number. Let's call this equation 1. Okay. What are these equations? What are the nature of these equations? These are non-linear partial differential equations for 3 variables: u, v, and p, and 2D, right? So you don't have a separate equation for pressure, but you have an extra equation. So these are non-linear partial differential equations for 3 variables. So this is what I'm going to do over the next 1 hour. I'm going to reduce this to a non-linear ordinary differential equation, a linear partial differential equation, then we'll have linear ordinary differential equation, and then we will study the linear ordinary differential equation, and the number of variables also will reduce. Okay, this is non-linear partial differential equation of second order, non-linear second order, because the highest derivative is 2. Okay, right? So there are many ways to approach this. For example, I could non-dimensionalize these equations if I want. Okay, well, maybe let's non-dimensionalize it. Okay, and let me do one more thing. I will basically I will introduce some to non-dimensionalize. I need to introduce some non-dimensional variables. Correct? So okay, so I'll say x is x tilde is x by L, y tilde is y by L, u tilde is u by capital U, v tilde is v by capital U. Okay, I will call it capital UC, so that it's a characteristic velocity. Okay, similarly, I'll take a scale for pressure. I'll take P tilde as P by rho UC square. I will take time as time by L by UC. So L and UC are characteristic velocity and characteristic length scale in the problem. Okay. Now, if I write down, if you substitute wherever there is U, I can substitute U tilde times UC. Wherever there is V, I can substitute as V tilde times UC. Tilde means it's a non-dimensional variable. Okay. Now, if I write down this Navier-Stokes equation, this is what I'm going to get: del U tilde by del X tilde plus del v tilde by del y tilde is equal to 0. Okay, because I'm a little lazy and I have the luxury of an iPad, what I will do is I will just copy and paste it here. It makes my life a little easy, and it'll, more important, it'll save time. Okay, if I do this, then if I do it correctly, then I will get a 1 by Reynolds number here, 1 by Reynolds number here. Okay, and all the other variables will have this tilde. Okay, this is my Navier-Stokes now. Okay, non-dimensional Navier-Stokes. Okay, now this Reynolds number is extremely important. You have to make sure that this Reynolds, if you have to do this very carefully, otherwise you will not get a non-dimensional equation. You will not get a Reynolds number like this. Okay. Now let's basically introduce a disturbance. How do I introduce a disturbance? That's a question. Okay. Now I could say, I could consider a flow like this. I could have a flow which is some flow like this. Okay, this is a flow in the x direction, but it is varying in the y direction, which means that I have a mean flow which is u is a function of y. You understand? Huh? I have a mean flow which is a function of y. Now I can think of various examples. For example, if it is a jet, what is a jet ultimately? It's a region where fluid is coming out at very high speeds, correct? So for example, if it is jet coming out of a nozzle like this, then the fluid, this is the jet coming out of the nozzle. The velocity profile will look like this. All right, got it? Same features. This is u is a function of y, but it is flowing in the x direction. Okay, right? If it's a boundary layer, flow over a flat plate, this is u is a function of y, but it is flowing in the x direction. Okay. In both these problems, the jet or the boundary layer problem, there is a small vertical velocity as well. The other component is also present, but by and large, we are ignoring it. The characteristic velocity is, the dominant velocity is horizontal. Okay, that's how I've taken it. I've also ignored gravity for now. Okay, just to illustrate the point, but I will not study the problem with gravity, but but we can come back to that later. Okay. Now, you have this, you have such a velocity profile. Now you see u is a function of the mean. This is called the mean flow, mean velocity, mean flow or base flow. For simplicity, we're also taking the mean flow or the base flow to be independent of time. Okay. What about these variables u tilde, y tilde, and u tilde, v tilde, and pressure? What about these UVP pressures? They are functions of space and time, correct? So now I can say it's a PDE, remember, right? So first is nonlinear PDE. So let's simplify it. So we'll say I have u tilde, which is a function of x, y, and t. I will write it as capital U of y plus some fluctuation, okay, which I will just call it as okay, let's call it as u hat of x, y, and t. Okay, if you want to be more precise, we can even say this. Okay, let me do it in a more rigorous way. We'll put a small parameter epsilon. Epsilon is very, very small. What does epsilon tell you? If epsilon is 0, then there is no fluctuation. I only have a mean flow. You got it? If epsilon is 0, I just have a mean flow, but I'm introducing a small perturbation to it. Okay. Similarly, I'll say V tilde, which is x, y, and t. There is no mean flow in the y direction. There is no vertical mean. There is only a horizontal flow. So there'll be no mean. There'll be epsilon. Sorry, there'll be 0 mean, but there'll be a fluctuation. Fluctuation is V tilde or V hat x, y, and t. And I can have pressure, some mean, which is a function of x, which varying in x, plus a fluctuation, which is p hat. Sorry, this is not capital P. Okay, typically we write mean quantities with capital letters and the fluctuation quantities with the small letters. Now remember, at this time, I'm not telling what is the form of the fluctuation. All I've said is these fluctuation terms, these terms here, these fluctuation terms. All I'm saying is these terms are small. And are small. How do I know they are small? Because epsilon is very small. Epsilon is literally the amplitude of those fluctuations in some sense. Is this clear so far? Okay. Now, let's introduce these fluctuations into the Navier-Stokes. Let's substitute them as it is. So I was wrong when I said that the earlier equation is not the biggest equation. This is going to be the biggest equation. Okay. Let's substitute them. Okay. Let's start with one by one. So del u by, what do I have for continuity? Del u tilde by del x. That is what I have in continuity, right? Huh? So del u tilde by del x becomes okay. This becomes del epsilon times del u hat tilde by del x. Okay. So that's the first thing. Okay. Now similarly, we can write down other derivatives. Del u tilde by del y. This is u, by the way. This becomes epsilon. Now, can anybody tell me what will be this term? What is the derivative of u with respect to y? The total velocity u with respect to y. I'm just taking the derivative. It will just become d capital U by dy. That's the first term, right? It won't be 0. Why would it be 0? U is changing with y, right? I have this quantity, which is y. Okay. I have this derivative plus I have epsilon. I also have a derivative with respect to u hat. So that will be partial u derivative by del y. Note that in the first term I wrote total derivative because capital U is a function of y alone. But in the second term I wrote partial derivative because small u hat is a function of x, y, and t, all the three variables. So I have to be partial derivative after that. Similarly, you can write other variables. Del v tilde I'm sorry, becomes del v hat by del x with an epsilon. Del v tilde by del y becomes epsilon del v hat by del y, and so on. Okay, you can take the second derivative and so on. If you substitute for all the variables and write down the full equation, this is what you're going to see. Let's give this a name. Let's give this as equation expressions 2. Okay, so substituting 2 into 1. What is here? I'm substituting this form of the solutions that I've taken into the full equations. Then I'm going to get I'm going to slightly more complicated equations, but let's look at those complicated equations. What are they? I will get del u hat by del x plus del v hat by del y is equal to 0. Okay. Then I'm going to get del u hat by del t. That's the first term. I have u del u by del x. I have capital U del u hat by del x. Remember, there's an epsilon here, epsilon here. Okay. Similarly, epsilon in both terms. Okay. I have this. Then I have del u hat by del x. Okay. I have the next term will be u del u by del y, correct? U del u by del y will be u del u by del x, v del u by del y. Okay, let's do one thing. I'm doing it a bit too fast quickly. Perhaps I'll just do it in step by step. Epsilon del u hat by del t plus capital U plus epsilon u hat del by del x of capital U plus epsilon u hat plus v. V is nothing but epsilon v hat del by del y of capital U plus epsilon u hat. This is my left hand side of the equation. Okay, I've just substituted wherever there is u, I've substituted u hat. Wherever there is u, I have substituted u tilde, I have substituted capital U plus small u. Wherever there is v, I've just substituted small v, that is epsilon small v. Okay, this is what I have. This is equal to minus del by del x of capital P plus epsilon p hat plus the viscous terms. Okay. Now, okay. I'll just write it that. Okay. We'll leave it at that. We'll not write the viscous terms right now. Let's look at this equation that I have. Okay. If I simplify it, what do I have? Epsilon del u hat by del t plus capital U. I have 4 terms that will come, but 2 of them will be 0. I'll have capital U epsilon del u hat by del x plus epsilon u hat del capital U by del x. That will be 0 because u is a function of y alone. Okay. And I have epsilon square u hat del u hat by del x. Is that all that I have here? U this is 0. Okay. And similarly, I have epsilon v hat del capital U by del y plus epsilon square v hat del u hat by del y is equal to minus del p by del x plus, or rather minus epsilon del p hat by del x. This is my full equation. Okay. Now what we will do is we'll look at the equation as it is. Okay, as it satisfies. Okay. So if I write down equations at order, so I can write down equations at the order epsilon. Okay. Order epsilon terms correspond to perturbations. Okay. If I set epsilon is equal to 0, then I will basically get only the mean flow because there are no perturbations at all in this, correct? So I am only looking at the first correction to the perturbations. Okay. Also, epsilon is much smaller than 1, implies epsilon square is much smaller than epsilon. So any terms which appear as product of perturbations is negligible. Okay. So if I do this, then this equation becomes epsilon, I'm only writing order epsilon equation, not the mean equation. Del u hat by del t plus epsilon capital U del u hat by del x, okay, plus epsilon v hat. This can be replaced as d capital U by d hat, d capital U by dy. I'm writing this term here, okay, and this term here is very small, okay. This is also very small. This is also very small. If I have minus epsilon del p hat by del x, or if I take out epsilon as arbitrary, okay, ignoring epsilon, what do I have? I have a simple equation del u hat by del t plus u cap del u hat by del x plus v hat d capital U by dy is minus del p hat by del x. Okay. Similarly, I can write down a v equation. What's the equation for v? You get del v hat by del t plus capital U del v hat by del x, okay, is equal to minus del p hat by del y. That's the equation for v. Okay. So all I have done is I have substituted wherever there's a very straightforward algebraic exercise. There's no complicated math or anything. All I've done is I've substituted for the total velocity. I've divided it into a mean component and a fluctuation component. Fluctuation is what I call as perturbations. I've also imposed that these fluctuations are small. Okay, so that product of fluctuations are even small. Okay, once I do that, I only have the linear terms in the perturbations. Okay, let's put again. So what we have is the linearized equation, that is del u hat by del x plus del v hat by del y is 0. That's the continuity equation. The x momentum equation is this one. This is my x momentum equation. And my y momentum equation is this. Notice that we've ignored, these are inviscid. We've ignored viscosity. Okay. I have ignored viscous effects. For now, the assumption is that the viscous effects can be ignored if my Reynolds number is large. Okay, if you look at the non-dimensionalized equations, 1 by Reynolds number is sitting in front of the viscous terms. So right, so if the viscosity is large, then I can ignore it. You can make some simple hand waving calculations. Even for a thin jet that is coming out of water, let's say you take the case of a water tap that is coming out in the home. Okay, this is a water tap, and this is your tap. This is the tap, right? If you open the tap, then you basically get a stream of water, right? You get a stream of water. You make an estimate of what is the velocity of this. What if you take a typical velocity of 1 meters per second? Typical diameter of the tap is, let's say, 1 centimeter. Okay, and you use the viscosity of the water. You will see the Reynolds number is in thousands. Okay, even for this system, the Reynolds number is so large you can ignore it. Okay, there are some problems where you cannot ignore Reynolds number. I'll give you a quick interpretation of why and where Reynolds number viscous effects cannot be ignored. But then we will only do with first we'll do with look at problems where Reynolds number can be ignored. Okay, is that clear? So this is what I have. This is now what do I have now is I have a bunch of equations now. What is the nature of these equations? We started with non-linear second order partial differential equations. Correct? Because I got rid of the viscous term, it's no longer second order. But is it nonlinear? Are these equations nonlinear? Are these equations any you can unmute yourself and speak. They're linear equations, exactly. Why are they linear? Dr. Jitu, why are they linear?
There are no u terms, u dou v by dou x, like those terms.
U dou v by dou x.
Dou u by dou x, like that, coefficients.
Oh no, I do have capital U dou u by del x.
Okay.
Do you mean to say there is no term which is like u hat del u by del x?
Yes.
So there are no product of the perturbations. You see, each of these quantities here. So what is unknown here? What unknown is u hat, v hat, and p hat. They are the unknowns. But what is known to you? Capital U of y is given to you. This capital U that you see here, this is given. This is already prescribed. So you're not trying to find it. Okay. So when these are linear partial differential equations for 3 variables. Understand? These are linear partial differential equations for the 3 variables. Okay. Now there are many things that we can do to simplify this system. Okay. Now the moment I have this, whenever I have a system like this, it's convenient to write it in terms of a stream function. Okay. Now notice that this equation, for those who don't know or not from fluid mechanics background, there's a very simple trick. Whenever you have an equation like this, del u by del x plus del v by del y, you can cancel this equation by defining one single variable. Okay. What is it? If I take u hat to be okay, fine, we'll do it this way. U hat to be, let's say, del psi hat by del y, and v hat to be minus del psi hat by del x. Meaning I've defined a new scalar psi, okay, such that the derivative with respect to y is going to give me u, the derivative with respect to x is going to give me v. Okay. And if I substitute this, you can clearly see that del u by del x is going to give me del square u by del x del y. Del v by del y is going to give me minus del square psi by del x del y. So automatically the equation is cancelled. So the presence of this continuity equation allows me to define a stream function. Okay, correct? So if I do this, then what is the advantage of this? One equation is gone straight away. I can also get rid of the pressure if I do it carefully. Okay, but let's first substitute it and see what we can do. Okay. So I have del by del t, u becomes del psi by del y. Okay. I hope I'm doing it right. Plus okay, let's continue. Capital U del by del x of u, that is del psi by del y, plus v. V is minus del psi by del x d capital U by dy is equal to minus del p hat by del x. Similarly, the other equation becomes del by del t of minus del psi hat by del x plus capital U del by del x. V is minus del psi hat by del x. This is my expression for V. Correct? So far looks okay to me. This is minus del p hat by del y. Okay. Now notice that if I want to, now I have two equations in two unknowns. Okay. This is unknowns are psi hat and p hat. I've got rid of u and v. I've written everything in terms of psi hat. I have two equations and two unknowns. Okay. I can reduce it to one equation and one unknown. How do I do that? If I look at the right hand side, I have del by del x at the top and del by del y on the right hand side for pressure. I can eliminate the pressure by just taking the y derivative of the first equation, x derivative of the second equation, and then I subtract one from the other. Okay. So in other words, what I'm going to do is I'm going to take del by del y of this equation. I'm going to take del by del x of this equation, and I'm going to subtract one from the other. So let's write down the derivative equations first, and then we'll subtract them. Okay. I'll change color so that you can see that it's different. So I have del by del t of del square psi by del y square plus, remember u is a function of y. So if I take the derivative, I'm going to get d capital U by dy. It's a chain rule. Del by del x, del square psi by del y. I'm going to get two terms here. Del by del x, del square psi by del y square. Okay. And I'm going to get one more term here. Minus del psi hat by del x, d square u by dy square, then minus del square psi by del x del y, d capital U by dy. This is equal to right hand side. Okay, this is my first equation. The second equation is becoming a little complicated, I know, but bear with me. It will become del x square. It will become simple very quickly. A lot of terms will cancel out and they'll get joined together. The second term would be plus u times, u is not a function of x, so I just have to take the derivative inside. Is minus del square p by del x del y. This is what I have. Okay. Now I can subtract one from the other. I'll choose yet another color. If I subtract one from the other, what do I have? I have del by del t of, I can combine the time derivative terms. What do I have now? I have del square of psi, where del square is nothing but del by del square by del x square plus del square by del y square. I can combine the two. Okay, that's the first one. So these two are done. Somebody turned on their audio, it's quite loud. Okay, next one, I'll combine the u terms. Okay, you see this here, del by del x and del by del x. U del by del x is common. If I combine them, I have u times del by del x of del square of psi hat. Yeah. I have those two. What else can I write down? Also note, if I subtract one from the other, I have the del square psi by del x del y. Okay. I have one more term which is plus 2 times d capital U by dy del square psi by del x del y. This doesn't sound that right. We made a mistake here. No. Okay. Sorry. I made a mistake here. So the two terms are already gone. Now what do I have now? You see this term here and this term here. These two will cancel each other out. Okay. These terms will cancel each other out. Okay. And finally, I'm left with the last term, which is del psi by del x minus del psi hat by del x d square capital U by dy square. Okay, this is equal to 0. Okay, the equation is actually simplified quite a bit. Okay, this is my full equation. Let's call this as equation maybe 3. Have I used 3 already? 2. Okay, we'll call this as 3. We'll call this as 4. Okay, so this equation is a single equation. Okay, now we can write this in a more compact form. You see del square psi is appearing 2 times. The Laplacian of psi is appearing 2 times. So I can combine them. I can say del psi by del t plus u del psi by del x of del square psi, okay, psi hat, minus d square u by dy square of del psi by del x is equal to 0. We'll call this equation as 3. We'll call this equation as 4. Okay. Now what is this equation? It's a non-linear. No, sorry, not non-linear. It's a linear ordinary differential equation for single variable psi. Is it linear or not ordinary differential equation? This is still an ODE, PDE, partial differential equation. Because psi is now a function of x, y, and t. Okay. So we started with nonlinear partial differential equations for 3 variables. From there we came to linear partial differential equations for 3 variables. Now we have reached linear partial differential equations for 1 variable. Okay, we have reduced the complexity of the problem by now bringing it down to 1 variable. But what is the sacrifice that I've made? If I look at here, these are all first order equations. There are no second derivatives, correct? But here I've got second derivatives, meaning I've gone from linear first order PDE to one single linear second order PDE. Okay, this is what I have, linear partial differential equation for one single variable. Now, what is the way in which you solve partial differential equations? Anybody? Let's take the case of a heat equation. Or let's look at the wave equation. Okay, del u by del t. How do you solve an equation like this? Anybody?
Hello, sir. Variable separable method.
You'll do a variable separable form, right? Variable separable form means what? You'll say this u, which is a function of x and t, is a function of t and a function of x. Correct? Now you can substitute this and you will get the solution which goes like u goes like some constant in some function of x minus ct. Okay. So the standard way of solving linear partial differential, one of the standard techniques of solving linear partial differential equations is to assume a variable separable form. Okay. Now we will try to use the same ideas. Okay. Again, we'll return to this equation that we have. Let me write down this equation again so that okay, this is my equation. Okay, this is my equation that I have. Okay, now this is psi hat is a function of x, y, and t. Correct? I will assume this. Now, remember the velocity is varying like this. The mean velocity is varying like this. Capital U of y. Okay, so which means that something is varying in y, but in the x direction, what about the x direction? I have not said anything about the x direction. We will assume the x to be infinite. So x, we will assume that it goes from minus infinity to infinity. So I have unbounded domain in the horizontal. I could have unbounded domain in the vertical also, but the vertical is not. But in the vertical direction, in the y direction, there is a mean velocity as well. Okay, so I will say that because y is special, the y direction is special, I will separate this out. First step, what I will do is I will say this is of the form. Let's just call it a psi of y. No, there's no more hat here. Okay, psi of y times another function of x in t. The question is, what should be the form of x in t? Okay, now in the morning, hopefully I convinced you that the language is waves. When we talk about fluid mechanics and stability, the language is waves. Now how do waves come? Now I want to bring in waves into this notion, okay, into the discussion. So I can say f of x comma t is representing what? So let's say I have a flow like this. I have a mean flow like this, and this, if there was no disturbance, then I will have streamlines going like this in a straight line, uniform flow. Okay, right? Now I am going to introduce a disturbance to the stream flow, to this. What kind of disturbance will I do? I will introduce a disturbance at every location in space. I will say that these streamlines will be oscillating like this. It will not be uniform anymore. It can oscillate. Okay. Now, if it has to oscillate, if these streamlines have to oscillate back and forth, now there are a bunch of things that have to be kept in mind. If I think about waves, what about the relationship between the waves from one y location to another? Are they out of phase? Are they in phase? I don't know. Okay. So I want to have the most general description. So first is I want to describe this to be a wave in the x direction. These waves can also amplify in time. Therefore, I want these waves to be, they want them to be in the form of waves in the y direction as well, and the time as well. Okay. So if I want wave in the x direction, I will say this is cos kx or sin kx. Okay. Those in the x direction. And in time, I have cos omega t, sin omega t. Okay. I could use these functions. These are the functions that we normally think about. Okay. There is another way to naturally think about this. If you want to approach the same problem from a more mathematical perspective, because this is x direction is the homogeneous direction, it's unbounded. Okay. I can basically immediately, the first thing I can do is I can take a Fourier transform of this equation. Okay. Right? And in time, I can take a Laplace transform in time. Okay. The moment I do this, I will get an ODE that I will get. Okay. But I'm trying to argue this purely from physical standpoint. Okay. So I want these. I want waves in the x direction. I want waves. So that the natural functions for an unbounded domain, smooth functions are sine and cosine. But I don't know what will be what sign it should be. Sine k, sine 2x, sine 3x, sine anything x. So I will call it as a general variable k. I don't know what is that k. Okay, k is just a arbitrary variable. It can assume any value. Again, I want it to grow or decay in time. I will call it as epsilon omega t or sine omega t or cos omega t. Remember, if I take sine omega t, cos omega t, it is only oscillations. If I want growth, I will have e power omega t. Correct? This is for growth or decay. Okay. So I want to combine all of this into one single function of f of x comma t. Okay, how do I do that? One way to do this is to say this f of x comma t, this is a postulate. It is a combination of all these functions. What is a combination of all these functions? E power I kx. I kx will be cos kx plus sin k, I sin kx. Okay, this multiplied by minus I omega t. It could be plus I omega t also, it doesn't matter. I can just change the sign of value of omega. I'm just writing it in the standard way that's normally written. This is cos omega t minus I sin omega t. Okay, this is usually the way it is. Okay, but you can also do where is growth in this? I can only see oscillations. Correct? So what we will do is we will further to get oscillations. What we will do is we'll say we will do what is called as in this right now in this lecture today. We'll do what is called as a temporal analysis. And to temporal analysis means we will say k is real. It belongs to the real number set, but omega is complex, which means that omega can be omega r plus I omega I. And therefore e power minus I omega t becomes e power minus I omega r plus I omega I of t. And this gives me e power omega it. Remember, that's why I took a minus there before the I, before the omega. E power omega, my I omega t, because I square is minus 1. I have e power omega rt with a minus I. So therefore, this gives me e power omega it times cos omega rt minus I sin omega rt. So this is the growth or decay part. And this part is oscillating part. So I want to describe a wave which can grow or decay at the same time oscillate as well. Okay. So think about if you throw a stone in the water, you'll see that the wave that you see on the surface of the water will travel. Okay. But it will also decay with time. The traveling part is coming from that oscillating part, which means that if you look at any point on the surface of water, it will just keep going up and down with time. And slowly it will dampen out. Okay, that is the oscillating part. And the decaying, the rate at which it decays is given by the first part, the omega it. Is this clear? Huh? In general, you can have all these complexities. You can have a growth or decay oscillation, and you can have, there is also, when you throw a stone in the water, there is a certain wavelength to the surface of water. There is a wavelength to those ripples. The wavelength of those ripples is given by the e power I kx, cos kx plus I sin kx. Okay. So if I put everything together, I now have f of x comma t is e power I times kx minus omega t. K is real, omega is complex. You can have other kinds of analysis, also called spatial analysis, where k can be complex, omega is real. You can even have spatio-temporal analysis where omega and c both are complex. Okay. But for now, we will just keep k to be real. Okay. Now, if I do this now, if I substitute, note that I don't need to worry about what should be before exponential. It could be any constant. I could take I have not put any constant. I've just put the constant that I put before exponential is 1, unity. Okay. The reason I've not put any constant is because it doesn't matter. Because even if I substitute this f here with any constant, if I multiply it with some constant into f, it does not matter to the solution because it will just get cancelled out in the equation above. That constant will not play any role. Okay. Is this clear? So therefore, there's no point in putting a constant there. Okay. So now this is the ansatz. Ansatz means that this is the form of the solution that I've assumed. Okay. Again, let me write down psi hat. Is it psi hat? Of x comma y comma t is psi of y e power I times kx minus omega t. Let's do some simplifications now. Okay. This is a variable separable form, remember, but only difference is it's a variable separable form of 3 variables. It's a separate function of x, separate function of y, okay, and separate function of time. Only it's just that exponential of a plus b is exponentially exponential b. So those two things have got combined. Otherwise, they are separate functions. Okay. Now let's take the derivatives, each of them. What are the derivatives we will enter in this? I have del square psi. Okay. Which is del square psi by del x square plus del square psi hat by del y square. Okay, let's first do the first part. Del square psi by del x square, you have exponential 2 times. Okay, so I have psi hat is a function of y. Okay, not psi hat, sorry. Psi is a function of y, so it will not appear in the first term. I have exponential 2 times. If I take derivative of exponential, I have minus it's like ik whole square e power kx minus omega t. That's the first term. The second term is the exponential is not a derivative of y, so therefore I have d square psi hat d square psi by dx square exponential I kx minus omega t. So this can be combined as d square psi hat by dy square minus k square psi hat, sorry, not psi hat. This is just psi. I can combine. This is the first one. Okay, and this is del square of psi hat. Okay. I also need one more on the right hand side. I have second term in this. I have del psi by del on my original equation that I wrote. It's taking a second to. The second term that I wrote, I have del psi hat by del x. Okay, let's write down that as well. Is ik del psi by del x e power kx minus omega t. Now let's substitute both of them. What do I have here? Oh, I forgot one more thing. I have the first term of the equation is del by del t of del square psi. Del by del t of del square psi hat. Is nothing but d square psi hat psi by dy square minus k square psi. This term here that comes here. Exponential derivative of exponential with respect to time, that becomes minus I omega e power I times kx minus omega t. Okay. So that's the derivative with respect to time. I also have to deal with u del u by del x, u del by del x of del square psi. Let's do that as well. U del by del x of del square psi. This is nothing but d square psi by dy square minus k square psi. I have ik of exponential of kx minus omega t. This is my next term. Okay. Now I can substitute the whole thing. Did I give an equation? Did we give a number to this equation? No, I've not given. Let's give a number to this equation. Let's call this equation as 5. So let's substitute into 5. Substituting into 5, what do I have is d square psi by dy square minus k square psi of ik. Okay. Not ik. Minus I omega exponential of kx minus omega t. The second one term, which is d square psi by dy square minus k square psi ik exponential of I kx minus omega t. That's the second term. And then I need to deal with the last term, which is on the last term in this, but is minus d square u by dy square del psi by del x. That is ik del psi by del x e power I kx minus omega t. This will be equal to 0. Okay. Now if I cancel out all the exponential terms can be cancelled out because they will never go to 0. Okay. I can also get rid of I in all the terms. If I do this, then I'll get a simple expression. D square psi by dy square minus k square of psi. This will be there has to be a u somewhere. Okay, there is a u here. Sorry, there is a u, capital U here. Okay, so there is a u sitting here. So if I take this u, I think I mixed up the colors. So let's basically write everything in black only. Okay, this will be ku minus omega minus d square psi by dy square times k into del psi by del x is equal to 0. Okay, and this gives me a simple equation for psi. Okay, let's write this down. I have if I divide throughout by k, I have u minus omega by k d square psi by dy square minus k square of psi minus, I don't know why this became capital U, minus d square u by dy square. There is some mistake I've made here. Del psi by del x should never have come. Why is there? Okay, I'm sorry about this. This should have been just psi. This should have been just psi. Okay, let's correct this. It should have just been psi. Okay, of psi is equal to 0. So here actually I made a mistake. When I take a derivative with respect to x in this equation, I basically accidentally took a derivative with respect to psi as well. Okay, psi is a function of y alone. Okay, and therefore I have this equation, and I can define a new variable. Omega has units of, omega is like a frequency, it has 1 by second, and k has units of 1 by meter, it's a wave number. So therefore omega by k has units of meters per second, which we'll call it as c. Okay, so if I define a variable called c, which is omega by k, I have u minus c. This will be d square minus k square of psi minus u double prime of psi is equal to 0, where d is nothing but d by dy and u double prime is nothing but d square by dy square of capital U. Okay, I've got one single equation for psi, and this is a linear ODE, because you see derivatives are only with respect to y. Okay, there are no derivatives with respect to x or time. This is linear ODE for psi. Okay, psi of y alone. This equation has a name. It's called the Rayleigh stability equation. Okay, or the Rayleigh equation. Okay, a single equation for psi will tell you what should be the the stability of this equation. If you're able to solve this equation for simple problems, then you can predict the nature of the flow. Okay, whether its flow is unstable or stable. I will basically tell you one simple problem. We will take one simple example. Okay, and we will look at the stability of this flow. Remember in those experiments we saw this tank experiments where the bottom was covered with some orange fluid. Okay, the bottom was covered with orange fluid and then it was tilted. These are the experiments where on the YouTube that I showed you at the beginning. Okay, I mean these experiments are available on YouTube. That's what I meant to say. They're available on YouTube. And if you tilt this experiment fluid, then all this fluid will go to the left and the lighter fluid will come to the right. Upper fluid will move up. So then you have this instability. Okay. Now, if I were to understand this instability, I will construct a very, very simple model of this instability. Okay. The very simple model of this instability is what is called as a Kelvin Helmholtz instability. Okay, the idea of Kelvin Helmholtz instability is locally, if you observe, if I take a small region here or anywhere in the middle, okay, between the two fluids, locally, how does it look like? I will take coordinate system which is x is in this direction, x is in this direction along the tilted thing, and y is vertically up. Okay, if I take such a coordinate system, I can define a local velocity like this. I can define a local velocity this way. Okay, I can call this as velocity is u1 and this is u2. Okay, in the example that we showed, u2 is negative and u1 is positive. Okay, but it does not matter. These are just arbitrary values of u1 and u2. Similarly, I could even have the densities also. Like typically the upper fluid will be lighter and the lower fluid will be heavy. So these are rho 1 and rho 2. Is this clear? Huh? Now, what is the biggest advantage of taking a profile like this? Okay, these profiles, if I look at these profiles and connect it to what we had in this equation, let's look at the Rayleigh equation. The Rayleigh equation is, it's a linear ODE, but it's a variable coefficient ODE. Why is it variable coefficient? Because I have u as a function of y here. This u here in general is a function of y. Okay. Further, I can reduce this to one thing I forgot, and maybe I should mention this very quickly. This, I'll mention it here itself. You can always reduce this equation to an eigenvalue problem. How do I reduce this to an eigenvalue problem? I can say, I can reduce this to u times d square minus k square of psi minus u double prime of psi is equal to c times d square minus k square of psi. Okay, I have just rearranged the terms, and if I now look at it, I have u times d square minus k square minus u double prime of psi is equal to c times d square minus k square of psi. This is of the form a capital X is equal to lambda b capital X. This is a generalized eigenvalue problem. Is this clear? It's a generalized, that's, we have reduced this to an eigenvalue problem. So you can think about, I mean, in an eigenvalue problem, whenever you solve eigenvalues problems, or when you teach your students what are eigenvalues and eigenvectors, many times the context is lost, because you don't really understand what is you don't connect the eigenvalues to something. And for example, in these problems, you can directly connect the eigenvalues to the growth or decay of the instability. Okay, that's what physically they mean. Let's come back to now. If you look at this, if you look at the Rayleigh equation, if you look at the Rayleigh equation, in general, this is a linear ODE but with variable coefficients, correct? Now, how do I make it into a constant coefficient equation? If I have to make constant coefficients, all I have to do is I have to simplify this capital U. Capital U is a function of y, correct? If I make capital U to be a constant, then it is a constant coefficient equation. Okay, that's exactly what we have done with this profile. If you look at this profile that we have taken, I can write this as u of y is equal to a constant u1 for y greater than 0, a constant u2 for y less than 0. And this immediately means u double prime is 0 everywhere except at y equal to 0. We'll come to that later. Okay. I won't be able to go into solving this problem. This is a standard problem in fluid mechanics. Okay, you'll find this in any of those textbooks. But I'll give you what do we get from solving this equation. Okay. Now you have this equation. Let's write down the Rayleigh equation. What is the Rayleigh equation? The Rayleigh equation is again u minus c d square minus k square of psi minus u double prime of psi is equal to 0. Now the good thing is I can solve this equation in two parts separately. For y greater than 0, u is a constant. Therefore, I have u1 minus c d square minus k square of u double prime. U double prime is 0 for y greater than 0. Therefore, it is 0. If u1 minus c is not equal to 0, then it means d square minus k square of psi is 0. There's a psi here. And this immediately gives me psi is equal to a1 e power ky plus a2 e power minus ky, because the characteristic equation will be lambda square minus k square is 0 and lambda equals plus or minus k, correct? Similarly, for y less than 0, u2 minus c d square minus k square of psi is 0, I immediately get psi is equal to, if I again assume u2 is not equal to c, I have b1 e power ky plus b2 e power minus ky. Okay. By imposing psi goes to 0 as y goes to plus or minus infinity, that's expected, right? Far away from the region of this instability, there is no reason for any disturbance at infinity, at very, very far away. So I can safely say at y goes to plus or minus infinity, psi goes to infinity. If psi has to go to infinity, psi has to go to 0. And that will only happen when a1 is equal to 0 and b2 is equal to 0. Because both of them are growing terms. Okay, for y going to infinity, a1 exponential ky will grow. Therefore, a1 has to be 0. And the other case, the other one has to be 0. b2 exponential minus ky will also grow. Therefore, we set b2 also 0. So if I now have, I have psi of y is simply a2 e power minus ky for y greater than 0. I have b2 e power, b1 e power ky for y less than 0. Okay. Now I'm not going to go into details of how we get k1 and k2, but I'll tell you what are the conditions that we could. Okay. We determine constants a2 and b1 from pressure continuity, pressure balance. Okay. And kinematic conditions. Kinematic conditions means if the fluid at the bottom pushes up, the fluid at the above also has to go up. If the fluid at the bottom goes down, the fluid at the top also has to go down. Okay, so that there are no voids that are created in the flow. Okay, that's one condition. One is a kinematic. That's just a geometric condition, kinematic condition. There's also a dynamic condition, which is that the pressure is equal on both sides, up and above and below. Okay, so by applying these conditions, you can find A1, 2. You have two conditions and two unknowns. You can find these conditions and you can get a simple equation for C or omega. Okay, so I will directly write down the expression for the C or omega. You will get omega, which is K into C, will turn out to be like this, which is nothing but K times rho1 U1 plus rho2 U2 divided by rho1 plus rho2 plus or minus rho1 rho2 u2 minus u1 whole square divided by rho1 plus rho2 whole square. This is the expression, okay, that we get. We'll simplify this a little bit. We will say I have a flow. Remember the experiment that I showed you. You have the lighter fluid is going up, the heavier fluid is coming down. Okay, let's assume that they are going up and coming down with the same velocity. Okay, which means that if u1 is equal to u, u2 is equal to minus u. Okay, that's the first simplification we'll do. We'll also assume rho1 is equal to rho2 is equal to some constant rho. Let's say we'll call it rho naught. Okay, let us simplify, meaning the two fluids are the same density. In general, it is not, but just for clarity, sake of clarity, I'm making that simplification. If you don't want to do that, you can work with a full equation, but I just want to highlight what do we get from this. What we get is, I get omega is K times, let's substitute it. Rho1, rho2 are same. So if you look at the numerator, rho1 and rho2 becomes rho naught. In the denominator, I get 2 rho naught. So I get u plus of minus u divided by 2 rho naught. That's what I have. Plus or minus I rho1 into rho2. What is that? So rho naught square. u2 minus u1. What is that? It will be minus u whole square divided by rho1 plus rho2. What is that? That will be 2 rho naught whole square. Let's simplify this. I have K plus or minus I. But just let make sure that I've done this. I'm doing this correctly. Just bear with me for 1 second. Okay, so far it looks okay. I have plus or minus this.
Harish, you want to continue for some time?
No. I just over.
Yeah. Okay.
I have rho 0 square cancels out. I have 1 by 4 u square. That is 2u whole square. That is 4u square. Okay. There is some goof up that I've made. I don't know. Oh, sorry. I don't know why I introduced an I. That's what was bothering me. Okay, there is no I here. Sorry, because there's no I in the whole expression. So this is what I have, and this can be simplified to plus or minus. The 4 cancels out. It just becomes K into U. That's all. Okay. And what it says is, if I want to plot the growth rate, it's just, you see, first of all, you see the solutions will be the solution for psi. Okay, that's the total solution for psi, which is x, y, and t, is now some function of y. Okay, e power I kx. That's fine. The second part is e power ku of t. That is omega, by the way. And this is positive. There is also a negative part, but negative part we can ignore because one way to say that it is decays with time, but there are other ways to actually argue that that is not the correct way to interpret. The negative part has no physical meaning, but we look at the positive part. It grows with time. Okay, which means, and if I were to make a plot of omega versus k, the growth rate versus k, how does it, sorry, versus k. Omega equals k into u. For any velocity u that I have, any velocity difference between the two, this fellow will grow linearly. Meaning this instability, once you have two fluids moving in opposite direction, you have an interface between the two, it will always be unstable. Okay, that's the Kelvin Helmholtz instability. What we saw in the experiment in the morning is, this is just a theory saying that any time the moment you create two flows which are in opposite direction, you will have an instability, no matter what. Okay, you will have an instability. But in realistic situations, there are some cases where this instability can be stopped or arrested. What are the first cases? If you have surface tension. Surface tension can prevent growth of some waves. Okay, very, very small waves will not grow that fast in surface tension. So surface tension will modify. If you have surface tension between the two fluids, like you do oil and water, what will happen is this curve will follow. It will be like this. It will grow here like this, and then surface tension will try to suppress the instability, which means that beyond this K, flow is stable. Okay, K is like the inverse of the wavelength, inverse of the wavelength. So these are small waves. These are long waves. So Kelvin-Helmholtz instability is a beautiful example of a long wave instability. Okay, all the small waves in general can be stabilized if you have surface tension, but there are many situations where you don't have surface tension, like salt water and fresh water. Okay, so in such cases, the only limitation of the theory is this initial condition, the initial profile. In reality, the profile is not like a discontinuity, it is a smooth function. That's the only thing which limits the accuracy of our prediction. But you will actually find that if you do this carefully, and you can actually do numerical simulations and you can do experiments, you can compare the prediction against this curve. This curve, omega, as a function of k, any plot like this is called as a dispersion relation. Okay, I will stop it here, and we will just to sort of summarize what we did in today's lecture, in the morning lecture and today's lecture afternoon. I first gave you examples of various instabilities and various systems where you are all the way from small scales to large scales where you get instabilities. Okay. And how many of these instabilities, the carbon vortex shedding was a nonlinear saturation of that instability. In the second session, we primarily looked at waves and how to look at stability. I introduced a lot of interesting concepts, absolute instability, convective instability. And then we derived a very important equation, which is a standard equation in stability analysis of fluids, which is called the Rayleigh equation. So just to reiterate the key steps, what we did is we started with Navier-Stokes. Navier-Stokes equations are nothing but nonlinear PDEs. We reduced it to a linear set of PDEs for multiple PDEs. Then we reduced it to a linear PDE for a single variable. And finally, we reduced it to a linear ODE for a single variable. So that's, you see, where we have gone. We've come from a nonlinear PDE to a linear ODE. Okay, using a sequence of steps. And each of those steps are built on certain assumptions and certain simplifications. And once we have this linear ODE, then there is hope to do some analysis. So we took up a simple problem of a two-layered Kelvin-Helmholtz instability. There's two layers, the velocity is a discontinuity, and we can get a dispersion relation, which tells you how does the growth rate vary as a function of wavelength. So in an experiment, you can actually see what is the wavelength that you're getting. So the wavelength, literally, in this experiment that you saw, the wavelength will be, you can check your prediction. How does it correspond to this wavelength? Remember, this wavelength is 2 pi by k. Okay, you can check, does it correspond to that wavelength in a real experiment? Okay, so those are the kinds of checks that you can do. Okay, and if it does, then it means your theory is all right. Okay, so in the afternoon session, we'll look at another very fascinating topic not connected to this. We'll look at perturbation methods to fluid mechanics, and we'll look at starting from simple ODE, how you can do some very elegant analysis and get some insight into how perturbation methods are useful to understand many fluid dynamics problems. Okay, so I'll stop it here.